So this is an exercise on finding the efficiency of a transformer when it's operating at full load. So it's exercise on the rating of the transformer. Effectively, it's actually finding the efficiency. So if we look here, the transformer is rated at 40 kVA, and this leads us to an important point, that the transformer is rated based on its apparent power. So a transformer is rated based on its apparent power S in units of volt amps or kVA. So that's an important conclusion from here, which is the rating of a transformer is based on the apparent power rating. And this transformer has feeds a load, and it feeds a load at a power factor of 0.8. So in effect, the secondary of the transformer is connected to an inductive load. An inductive load, and because it's lagging, we conclude that the load is resistive, inductive, and so this load has a power factor of 0.8, and it's lagging because it's an inductive load. So the transformer is feeding this load, and we assume it's operating at full load. During its operation, it's incurring two types of losses. So it's incurring copper losses to the value of 800 watts at full load, and it's incurring core losses, or also known as iron losses, at a value of 500 watts. We need to calculate the efficiency of the transformer at full load. So we have two types of losses. Copper losses, sometimes we refer to them as I square R losses, and we have core losses, also known as iron losses, and these losses are variable, so they vary with load. So as the load changes, they vary, and the core losses are constant losses. So in order to calculate the efficiency, we can think of the transformer as having input power, Pn, output power. So this is the useful power that is fed to the load, and internally we have two types of losses, copper losses and iron losses. So the way we would proceed is to find the output power. So the output power is equal to the power factor multiplied by the apparent power, which is 0.8 times 40 kVA, and that gives us 32 kilowatts. That's the output power that's fed to the load. And then we know that the losses are, so the input power is equal to the output power plus the losses incurred. And these losses are split into copper losses and core losses. So this is actually 32k plus the copper losses are 800 watts plus the core losses 500 watts, and that gives us 33,300 watts. That's the input. And so the efficiency, and we must make sure we clearly state that the efficiency is at full load or 100% load, because the efficiency will vary as the load varies. So this will be equal to the output power divided by the input power, and that's equal to 32,000 divided by 33,000, and that's approximately equal to 96%. So 96% is the efficiency under full load conditions.